Welcome back, Padres. Today, we're going to look at an honors problem involving conservation of energy. And we have a car that is driving off a cliff, and we're looking at how fast is the car going after it's fallen 100 meters, and how fast is the car going right before it hits the ground. So let's get started. So we're going to begin by drawing a picture. We have a car, and we know a few things about the car. We know the velocity at the top is 20 meters per second, and we know this total height is 400 meters. And we're trying to figure out how fast it's going after it has fallen 100 meters. So right at this point, we are trying to find the velocity. And so we're going to use energy. So conservation of energy says that all the energy at the top has to equal all the energy after it has fallen 100 meters. Okay, so we're going to compare the energies at those 2 points. So at the very top, it has potential energy, gravitational potential, because it has a height. It also has a kinetic energy, because it's moving. After it falls 100 meters, it also has 2 types of energy. It has a gravitational potential energy, because it has a height, and it's moving, it's falling. So it also has a kinetic energy. All right, so I'm going to break these up. I'm going to say mass times gravity times height plus 1/2 mv squared. It's going to be mass times gravity times height plus 1/2 mv squared. And this is still going to be the left side of the equations at the top, and the right side after it's fallen 100 meters. All right, let's start plugging some numbers in. Okay, so we're going to have 1,300 is the mass. We're going to use 10 for gravity, 400 for the height. At the top, it's going 20 meters per second squared. All right, so you'll notice I left out one thing. I left out that height. And you might be thinking the height is 100 meters, but it's not. The height that I'm looking at right here, this h, is not 100. If you look at our picture, the height is measured off the ground. So the height would be there, and that distance is 300. So I think that's one of the trickier parts about this problem is don't let that 100 deceive you. It's fallen 100, but the height is actually 300. Okay, so once I'm here, I am going to cancel 1,300 because it is in every single term. Keeps my number smaller. And so I get 4,000 plus 1/2 of 400 equals 3,000 plus 1/2 v squared. And so I'm going to take half of 400, which is 200. I'm going to add it together. All right. I am going to subtract 3,000 from both sides. So I get 1,200 equals 1/2 v squared. And now I'm going to multiply both sides times 2. I get 2,400 equals v squared. Take the square root of both sides. And I get v equals 48.99 meters per second. All right, awesome. So now I'm going to do the second part. The second part says, how fast will the car be falling right before it hits the ground? So let's do it. So I'm going to say, in a similar fashion, that the energy at the top has to equal the energy, all the energy at the bottom. At the top, it has the same as it did last time. At the bottom, though, it has absolutely no height. Height is 0. So there is no potential energy. All the energy is going to be kinetic. So our equation is a little bit different. All right? We are still going to cancel the m's, because there's an m in every term. And if you remember, the energy at the top, if we scroll up on the left side, even after I canceled my 1300s, my energy at the top turned out to be 4200. So I'm going to use that instead of redoing it. I'm going to say my energy at the top is 4200. And then my energy at the bottom would be 1/2 v squared. Of course, you can still plug all the numbers in and you'll get the same thing. I'm just trying to do a shortcut here. I can multiply both sides times 2. And I'd get 8400 equals v squared. Take the square root of both sides. And my final answer is B equals 91.65 meters per second. All right, that about wraps it up.